Okay, today we're going to be taking a look at basic trig ratios. These are the ratios sine, cosine, and tangent, and they relate to our navigation around right angle triangles. I have to stress this is for right angle triangles only, meaning each of these triangles features a 90-degree angle in them. Okay, so where do we have here? There's a little bit of opening problem teaser for you. Imagine standing out somewhere on the ground, looking at some place that's high in the sky, but largely inaccessible. Like they even have drawn a lake here to show you that you can't really take any good measurements here. Is it possible to determine the height of this, even though you can't reach it? Well, the obvious answer is yes, you can, although we may not know yet how to do it. It can be done. And a lot of the principles of trigonometry allow us to use achievable measurements to project what other measurements might be. So there's a bit of a reward for hanging around and learning some trigonometry. They went on to, gave further details about what's going on in all these spaces here, which would ultimately allow us to figure out the problem. But we do have to know some trigonometry first. As you probably have seen in a younger math class, out of grade 9 or 10, that there are three trigonometric ratios, and they are called sine, cosine, and tangent. They're abbreviated with the three-letter abbreviations here: sine, SIN, SOS, SCOS, and TAN. Sine, cosine, tangent. And what it does is it harnesses the information from similar triangles to produce a ratio. So rather than taking a look at any individual angle here, we consider the ratio of two sides that sit in the same triangle as the known angle. And from there, we can work out what other lengths of sides must be. So let's take a look at some examples of this, shall we? Before we get started here, I need you to take a look at your GDC. We're going to have to make sure it's ready to produce answers that we understand. So you go to the document, meaning it's going to be set in degree mode. Down here to settings, change the document settings, and make sure that the angle measurement in the second drop-down menu, well, first off, the rounding off, just float, and the angle measurements are set for degrees. Sometimes it will say one of the other two, radians or gradients, just change it back to degrees. And that's it for that. So if we're going to be finding sides in a right angle triangle, meaning there's some missing side information, some missing lengths, we don't get a ruler out and measure it because these diagrams that we make aren't accurate enough in order for measurements to be believed. So we use the symbols, the numbers, and the measurements inside them that are stated to us. If you're in a right angle triangle and you are given another angle, then you can find out the third angle by using the angle sum principle that all the angles add up to 180 degrees. Or if you want another side that's missing, you are going to have to resort to trigonometry. And that's what we're going to do right now. Okay, here's the conventional steps. If you're given a question, you typically redraw the triangle and you adorn them with the titles opposite, adjacent, and hypotenuse, depending on the angle that you're going to be using as your pivot point. After you've done that, you got to work out which is the correct trig ratio to use, and I'll give you some guidance on that. Set up an equation and solve it. And so we've got your GDC ready. Here we go. Here's a couple of different questions. They want us to work out the missing side lengths in H of A, B, and C. So for the first one, I need to work out that, well, the pivot angle, or the angle that's going to be of use to us, is this 61-degree angle here. The side length that we're going to be using is this one here, and it's the hypotenuse, which I can tell because it sits across from the right angle. So the one that I'm looking for is this one. Now, how do we come up with a name for that side length? It's not arbitrary, it's quite specific. It has to do with its relationship, it's where it sits compared to the known angle. In this case, that side length that sits across from the 61-degree angle, so it's across, and so that means I've got, sorry, it's opposite, and so you can see here that I've got the adjacent side and the opposite side, and that indicates that it's going to be the sine ratio. So I write down that the sine of 61 degrees is the opposite over the hypotenuse, and I cross multiply and solve, and I can see that it's 6.997. In this next case, the angle sits here and the unknown is here. It's not the hypotenuse because the hypotenuse is across from the right angle. So this one here is not on the opposite side. It's on what we call the adjacent side. So what do I have? I've got a 47-degree angle with an adjacent and hypotenuse. That is a cosine question. And so what I end up with is the cosine of 47 is the adjacent over the hypotenuse. And that solves to 7.5. If you need any help with how entering this on the calculator, just let me know. And lastly, you've got this angle here. This is the opposite side, but we're not given the hypotenuse. We're given the adjacent side. So if we're dealing with opposite and adjacent, that indicates the tangent relationship. Tangent is opposite over adjacent, and you can see now that I've got this solution here. Let's take a look at how I would do that on the calculator. Get a calculator screen going here. The trig center is in this area here. And you can see if you want to use sine, like in this first question, 8 times the sine of 61, 6.99695 is what I had. Second case, it was 11 times the cosine of 47 degrees. That yielded that answer. And lastly, it's going to be 3 times the tangent of 69 degrees. And just hit enter, and it will give you the answer that we need. And we'll deal with rounding off issues later on. Here's 3 more to try. In this case, we're still finding sides. We're finding a hypotenuse. We're finding an opposite. And we're finding another hypotenuse. But the information that we're going to be using changes from question to question. So take a minute to try and work out what those ratios are. And I'll take a look at the answers later. Here's another set. I'll go ahead and work these out here for you. Just do it very quickly. You can see that in this first case, it's tangent because in relation to the 67-degree angle, we've got opposite and adjacent. In the next case here, we've got sine because we have opposite and hypotenuse with relation to that 36. And in the last case, we're back to tangent again because this is the opposite and this is the adjacent side. And we have to be a little bit tricky with the way that we're setting it up. Notice it's not always the variable that takes the numerator position. Sometimes it also takes the denominator position too. At any time, of course, you should feel free to hit pause, stop, and maybe go back and hear the words again or see what I've done again on my calculator screen. Once again here, this is adjacent and hypotenuse, that's cosine. In this case, it's opposite and adjacent, that's tangent. Oopsie. And in this last case, it's adjacent and hypotenuse, so that would be another cosine question. And again, hit pause, make sure you know what I've done. If not, ask me lots of questions. Okay, so that was how we find the lengths of sides. What if we want to find angles? In this case, we have to use the inverse of the sine, cosine, and tangent buttons, but they're located in the same trigonometry center on our calculator. No worries. So instead of finding out, so that the angle that we're going to find is going to be trapped within one of these ratios, and to unleash it, we perform what we call the inverse sign on the opposing side over here. Make more sense when you see an example or two. So you can see in all of these cases, they've indicated an angle that's unknown, and they want you to find out its value in degrees. So for this angle here, theta, the relationship is this is the adjacent side to theta. This is the hypotenuse of the triangle. Adjacent hypotenuse indicate cosine. So what I'm going to do is I'm going to write down first off that the cosine of the angle is 4/5. So read another way, you change it around by saying the angle can be found by performing the inverse operation of cosine on that same 4/5, and you'll get that answer. Now I'll show you that on the calculator in a second. If you go to the next one here, this is the opposite and the hypotenuse, that's sine. And lastly, this is going to be the opposite and adjacent, so that's going to be tangent, as you see there. On our calculator, let's take a watch of this. Still go back to the trig center, you'll inverse cosine now, and put the 2/3 in there, 4/5, and there's your angle. This next one is a sine problem, inverse sine of 3/4. It's funny to note that they change it back into a fraction, even though you hit 4 divided by 5 and 3 divided by 4 in those last two questions. It reorients it into a fraction for us, which is quite handy. You can try these ones now. Hit pause, give them a try, and my answers will pop up in a second. Okay, here's my answers now. Okay, I hope you got those. Here's 3 more. Please give them a try. Hit pause. Okay, I'm right back now. Here's my answers. Check those against mine. Okay, so that's how we find either the sides or angles in right-angled triangles. The complexity of this is going to jump. We're going to be dealing with non-right angled triangles very soon. But for now, we're in section 1H of our textbook. You see there's questions 1, 2, and 3, and the questions that you're asked to do are right here in section H, and we can do those together in class, or you can do them on your own. Okay, good luck.